Okay, this is a nice challenging problem from the end of chapter 13. It's a colligative property problem, and we're given 2.5 grams of an unknown, and we're given the empirical formula, which is kind of cool. That's like a throwback to chapter 3 or 4, I think. And we're told that we take 2.5 grams of this unknown, we dissolve it in 25 grams of benzene, and we measure its freezing point. And from that information, can we figure out the molar mass of the solute and its formula? And the answer is yeah, sure we can. Now, how do you do these kind of problems? Normally, you have to kind of decide, well, given the information that I have, what kind of things can I calculate? And then the more things that you calculate, the more of a nudge you'll get in the right direction to figure out the answer. We want eventually the molar mass and the formula, but some of the things we can do very quickly, we can calculate the freezing point depression. And we can look over in the chart on the side and we can see benzene normally freezes at 5.5 degrees. And so in order to calculate the amount by which it's depressed, we subtract the two values, the 4.3 away from the 5.5, and we can see that that's 1.2 degrees C. So it's gone down by that. What else do we know? Well, we know an equation that links the freezing point depression to the molar concentration. And in this problem, we've just calculated the freezing point depression, and we can look up the freezing point depression constant for benzene. And so that suggests that what we can do certainly is calculate the molar concentration. And we can just rearrange, and so molality then is delta T over Kf. And again, we've calculated delta T. We can look up Kf, and the units are going to end up with molality. And probably in terms of significant figures, we've got 2 and 3, so we probably can only write 2. But even though my calculator will spit out all the digits, we really should keep the first 2 significant. And again, I would like to go ahead and keep an extra digit, the 4 on the end. I'm going to call it guard digit. And that's just because I can see myself doing a whole bunch more calculations here, and I'm super worried about that limiting our final answer and leading to round off error. So that's the concentration, 0.23 moles. And we can rewrite that as a conversion factor, and that's 0.234 moles of our solute, which we'll call X, over each kilogram of benzene. Okay, so just like molarity is moles per liter of solution, molality is moles per kilogram of solvent. So if we look back at the problem, we didn't have a kilogram of benzene, did we? We had 25 grams of benzene, and so that means that we can calculate how many moles of our unknown were in our 25 grams of benzene by using that conversion factor. So that's our 25 grams of benzene C6H6, and we can convert grams into kilograms, or we can shift the decimal 3 times if we want to, and then we can use this as a conversion factor. And so we've got 0.234 moles of our unknown in every kilogram of benzene. And so we can use this to figure out, well, how many moles of our unknown did we actually have? And the answer is 5.86 times 10 to the minus 3. Okay, so one of the things the problem wanted us to do is to find the molar mass. And we know the molar mass, which we can write fancy with that's curly M, is the number of grams in a mole, or more generally, the number of grams divided by the number of moles in our sample. And if we look back at our problem, we had 2.5 grams of our unknown, and we've just calculated that that was equivalent to 5.86 millimole, or 10 to the minus 3 of a mole. And so that means that we can go ahead and actually calculate the molar mass, 427 units grams per mole. Okay, so that's pretty cool. So we figured out our molar mass. The problem also wanted to know what's the molecular formula, and we were told the empirical formula. And remember, the empirical formula is the simplest ratio of the atoms. And so in our molecule, we had 6 carbons to 5 hydrogens to 1 phosphorus. And our molar mass is 427. So the question is, what's the mass of the empirical formula? Well, you got 6 carbons and 5 hydrogens and a phosphorus. And if you look up those masses and fill them in and add them all up, phosphorus is the only one I actually had to look up. I'm not too familiar with phosphorus. I get 108.07, and so that's how many grams one molecule of C6H5P would be. But since it's an empirical formula, it could be that, it could be 12 to 10 to 2, or 18 to 15 to 3, or so on. So we need to figure out, I guess, how many times the empirical formula goes into the molecular formula. And so we can just divide those two numbers, right? And so if we know the molecule as a whole has a weight of 427 grams per mole, and we know that each unit of our empirical formula is 108, then we can see how many times the empirical formula must be copied to get the molecular formula. Now, I get 3.95 when I do this, and we can see that that's probably close to a whole number 4. So that means that we can take our empirical formula and kind of multiply it by 4. So that means that we've got 24 carbons and 20 hydrogens and 4 phosphoruses in our molecular formula. And that's the end of the problem.